There we go. Guys, so what we do is we push the mode button, and you guys have all done quite a bit of stuff here. We've done radians, degrees, you've maybe even done some of the real and imaginary complex stuff. But down here, just below radian, it says function, and then off to the right, notice it says parametric, polar, and then sequences. We will actually use all four of these this semester. So you've probably only ever done function and maybe polar, right? So maybe you've done polar, maybe others have not. So we're going to do parametric mode. So go ahead and hit enter on parametric mode. And once you've done that, if we kind of flip back to the notes here, the notes say, we're going to start with an example from the first semester. So we're going to enter these into our y equals menu. So I've got 5 cosine t and 0. So I'm going to just remember those. You guys have those on your sheet there. So we're going to go y equals. And as soon as you hit y equals, you notice that it's different, right? It says x1t, y1t. Normally it just says y1, y2, y3, etc., right? So this is obviously, right away it's different. So did I say make x1 5 cosine t?
Yes.
Okay, so 5 cosine of t. Notice this time when you hit the xt theta n button, it does not show up as an x, it shows up as a t. Typically t would stand for time. That's what it would stand for here as well. And then we said y1 was 0. So if you guys remember, I said this is sort of an example from the first semester. And you're going to see this. We'll try to connect it with that first semester here in a second. But I think there's one more thing it says here. Oops, let's go with this. Yeah, so it says highlight the slash on the left and press enter twice. The slash should now be the O or the little open circle.
Oh, I got that.
So we're going to do that. We'll go over here. Go over here to the left. Do you see the slash there? For me, it's blinking now. Hit enter twice. Oh, no, it's not enter twice. It's something different.
Go down and then go over twice.
Down and then over. There we go. Now it's just a little circle. I think I maybe wrote these directions. I think I maybe wrote these directions for a previous calculator operating system. I'm just going to do the little circle right now. Okay. We'll switch it over to the circle with the line for other things. But everybody have that? Okay. So we go down and we hit OK. Now we got that. And then doesn't it tell us to mess with our window a little bit? It says window needs to go from Tmin, is it 0 to 30? So Tmin is 0, so that's already there. Tmax is 30. And I think it tells us to leave everything else the same. Although I'm going to make my xmin, I'm just going to go plus minus 10 for my xmin and my...
Wait, what should I t-step?
Just leave, what is your t-step right now?
7.5.
That's really fast.
7.5?
Yeah.
Ooh. Yeah, I would go, let's go like 0.13. It doesn't have to be that long old nasty number. Keep it small like that. So let's see here. I'm going to go negative 10 to 10. And we're going to do a lot of messing around with the calculator today. Because there are, I think, a decent number of you that have never done parametric stuff before. Or maybe you did a long time ago. So we're going to explore a lot with this. Okay, so finally I think we're ready to hit graph. Is that what it says in the instructions? I don't have it up in front of me, of course. So when you hit graph, this is going to be very time dependent. So please don't push graph and then get distracted and look away. You're going to want to watch what actually happens when you hit graph. So, you ready? You can watch on mine, you can watch on yours. So that little blue circle is going back and forth, isn't it?
Yeah, I saw that.
Back and forth, back and forth. And once you get to t equals 30, it'll stop eventually. Just going and going and going. La 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 la.
What is a parametric?
Anybody stop yet?
Yeah.
Oh, mine just stopped. It's gone now, right? So if you think about what's going on, wouldn't that open circle represent like the proverbial particle moving around on the x-axis that we saw in the first semester? I mean, how many problems have we seen? An object, a particle, is moving around on the x-axis back and forth, and what's the speed at a certain time, or what's the displacement, or whatever. What's the acceleration at some particular time? Isn't that what that was doing? This particle is moving around back and forth on the x-axis. And we did that a lot in the first semester. We did that a lot last year for those of you who had AB before. So I want you to know what we're about to do is not really that much different than we've done in the past. The only thing we're going to do next is we are going to, I'm going to double check my notes to make sure I'm not skipping anything important here. What we're going to do next, did you notice we made the y1 equal to 0? That means the y component of movement was just 0. That's why it went left and right only. But what if we release that y component to be something other than 0?
Like physics.
It might move up and down in addition to moving left and right all at the same time. That make sense? So let me check my notes here and make sure that I'm not skipping over something I didn't want to skip over. So we did that. Okay, yeah. So now we're going to change from one-dimensional motion to two-dimensional motion. So please go back to the y equals and notice that it says x1 equals 5 cosine t. That's exactly the same as what we just did. But now instead of y1 being 0, we're going to make y1 natural log of t. So I will try that as well. So natural log of t. And it does tell us to mess around with the window a little bit, so let's do that as well. The window, let's see here. T steps 0 to 15, 8s and 3s. Okay. Okay. So guys, hope you're doing this with me. You're probably going to be a bit faster than me. This is a little bit awkward. I think this is, okay, the x's are the 8s. Okay, so negative 8 to 8, negative 3 to a 3. I'll leave that alone until we're kind of, everybody's had a chance to get there.
No, what do I want my x scale to be?
So according to what I wrote in the notes there, negative 8, oh, x scale would just be 1. X scale and y scale will both be 1. Yeah. Okay, so remember, before we had x1 being 5 cosine t, and I suppose predictably, since it was cosine was governing the x movement, wouldn't it just go back and forth? Right? Doesn't cosine just go from negative 1 to 1 over and over and over again? Now it was a 5 cosine t, so didn't we just go from negative 5 to 5 to negative 5 to 5, back and forth, back and forth? But now the y position function is not going to be 0 like we had before. It's going to be ln of t. So let's think about what ln does. Like, so if it's ln of t, if you start plugging in like 0, 1, 2, 3, 4, 5, doesn't it have this shape? Doesn't it move up consistently? So what would you guess the motion of this particle is going to be? It's still going to go back and forth, isn't it? But while it's going back and forth, it'll also go up to some degree, right? So let's see what happens. You can watch that little O. I think I left mine as the little O, the little circle. So I hit graph, and it's moving up, and a bit left and right, and up, and left and right. But notice that the higher it gets, the less extreme the upward movement. And doesn't that make sense with ln of t? Right, because that kind of flattens out as you go. Check this out. Let's go back to y equals, and let's do the thing that Hayden was suggesting earlier. Let's scroll off to the left there, where we got the little open circle thing. Hit enter, and let's scroll down to where we've got that little open circle. But instead of open circle, let's do open circle with a line. What this will do is this will track the motion. It'll leave like a little breadcrumb trail of where it went. You can kind of see that. So once you do that, hit OK. Question, Hayden?
Mine didn't go back and forth.
Okay.
Like when I pressed it, it was just like the ball, but it just went up.
Okay, so hit your y equals. What do you have for your x1?
5 cosine t.
Okay, t. Let's see here. Let's go ahead and graph. Okay. So let's go window. What's going right now? Just change it a little bit. Go like negative. Just change it a little bit.
Are you in radians? I'm in radians. I thought.
Did anybody else have the same thing happen as Hayden? Where the, ooh, that could be it. Let's see. Thank you. That's the most obvious answer. I should have thought of that. Thank you, Will. Try it again there with the radians, and that should do it. There we go. Hey, so guys, if you haven't graphed it already, you can look at the graph here. You can see that when you do the circle with the little line, it leaves the little path that it takes. You can see that it goes very steeply up at the start, continues to go left and right, and then kind of flattens out near the kind of the top of its motion there. And so this would be maybe a point where you could look at this. Maybe I could ask you a question and say, is that graph the graph of a function? What would you say?
No.
Not in the classical sense of a function, right? I kind of was very general. I said, is it the graph of a function? If I would have said, is y a function of x?
No.
You can definitely say no.
Because pencil
Right?
test.
But here's the truth. These are called parametric functions, right? So how could that thing be a function? Because it doesn't pass the vertical line test, that we all learned. Here's why we can still call this a function. The reasoning is that y is a function of time, and x is a function of time, but y is not necessarily a function of x. See what I'm getting at? And so we're going to kind of broaden our perspective on what a function is. Y is definitely not a function of x. This does not pass the vertical line test. But y and x are both functions of time, or t. Make sense? Okay, so in your notes, I think it says something along the lines of just mess around with this a little bit. So let's see here. Yeah. So mess around with the t-step. Mess around with the t-min and t-max. Listen, I want you guys to take like 5-6 minutes and literally just play around with it and see what if I change the t-step to this, what happens? What if I change the t-min and t-max? What seems to happen if I do that? I really just want you to mess around with these things, okay? And see what happens, right? Ready, set, go. Mackenzie, what's up?
I was just going to ask.
I've had this question twice, so it's probably worth addressing. The question is essentially like, what is the t-step doing? Remember I told you like when you hit the little circle with the line, the circle with the line, like the line shows you the path that the particle went on. The t-step is telling you basically how frequently to drop a breadcrumb. Right? So if the t-step is pretty small, like 0.1, which is about what it was, at least for me, that means like every 0.1 seconds, drop a breadcrumb. So it's like breadcrumb, 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 over and over and over and over again, right? If you say t-step of like 1 or 2, that's saying drop a breadcrumb every 1 or 2 seconds. And so there are going to be a lot fewer breadcrumbs. So for example, like if I start right here, and I make this, think about it like this. If I start right here, and I make this loopy path over to here, and stand right here, I took a loopy path, right? You could all see me real time doing that. And if I drop a bunch of breadcrumbs, if I just go, breadcrumbs over and over and over again like this, then if you were to come up here and look at my path of breadcrumbs, you would see that path, right? So that would be a t-step that's pretty small, like 0.1 or 0.2 or something like that. But if we set my t-step to be like 3, that would be like breadcrumb, breadcrumb, and that's it. It would almost look like a straight line, wouldn't it? So the more breadcrumbs you drop, the more precise your graph is. But as some folks have learned, the smaller the t-step, it takes forever because you're dropping a ton of breadcrumbs, right? It would take a long time for the calculator to like register all those little breadcrumbs. So a huge t-step is going to be a really inaccurate picture, right? It's going to, I don't know, maybe if some of you have done that, it almost looks like zigzaggy lines, or it might even be discontinuous or something. If you have a really tiny t-step like 0.0001, it's a beautiful graph, but it takes forever. That make sense?
Why isn't it working? Is this
What if we did go back and we said, all right, window, we're going to leave everything the same, but we'll might make our t-step like 3, like I said. Let's see what that looks like. You know what it should look like. Let's see what a t-step of 3 does. Didn't you lose the entire lower part of the graph? You didn't get a chance to even drop a breadcrumb on that lower part of the graph, and everything is straight lines because you only got to drop one breadcrumb every little bit. And so that's why like a higher t-step, like anything over 1, you're probably going to get a pretty choppy graph because it's not going to be able to drop enough breadcrumbs for it to actually make sense. By the same token, if we did what was suggested, made our t-step super tiny, like a whole bunch of zeros and a 1, this is going to be a much better graph. But look how, too small of a t-step, right? It wouldn't even take it. So let's go, what do you guys do, like 0.001? Something like that? Should take that. Okay, so there it is. It's going, it's dropping a lot of breadcrumbs. It's going to be, should be a pretty good graph, but it's really slow. Right? It's painfully slow because you got to reach into your bag and drop more breadcrumbs. I'm being silly, of course. The calculator is struggling to get all these things registered in any kind of a timely fashion. That makes sense? Okay. Then, some other things that I would like to do. I'm going to put my t-step back to 0.1. Mackenzie asked a really good question. She said, why does the graph stop? It's because of the t-max, right? So what if I wanted to see a lot more? What if my t-max instead of 15 was 50? So 50. I'm pretty sure I'm going to have to make my y-max quite a bit higher to see this. So maybe I'll go with like 15 or something. I don't know if that's going to be enough. So now it goes back and forth. It's just going to go for a longer period of time, so it'll get a little bit higher vertically on the y-axis. Just going to be able to see more of the path, right?
Is this how people write? Do they write equations to write messages on the calculator? Have you ever seen that?
Sure, yeah, you could do that.
Mr. Anderson, I think I broke my calculator.
Oh no, I thought I broke mine for a second there. What does yours say?
Oh no, but it clears everything.
That's right. It said. Mine's, okay, finally stopped. You can see that the motion ended there. Yeah. There you go. So you can also mess with different functions as well. Like what if we went back in here? Obviously the x was very cyclical, right? It was 5 cosine t, so it was going to go left and right a lot. What if we flip-flop the x and the y? What if we said, all right, let's make the x ln of t and the y 5 cosine of t.
No, not like that.
So if you hit that for a graph, what do you think is going to happen here? It's going to be the exact same kind of motion, just rotated 90 degrees. So if you hit enter there, get something like that. Tess, what were you going to say?
I was just going to say I don't get what's happening.
Well, you missed the first 10 minutes of class, so that's partially the issue. So you might want to go back and watch the video for the first 10 minutes of class. I'm not being trite. I'm just saying we talked about particle motion. This is just building off of first semester where a particle moves along the x-axis, right?
Yeah.
Now it's free to move up and down as well as left and right.
But what is a parametric function?
So yeah, parametric function, like the word parametric is based on the word parameter. And so usually, with all the functions we graphed in the past, the parameter for y was x, right? Y depended on x. Now, both y and x have a parameter of t. Y and x both move according to time. And so that's what a parametric is. Now, we could take this another level, which we won't in this class, but we could say, hey, you know what? A parametric function could also describe three-dimensional motion too, couldn't it? Couldn't we have a y, like an x1t, a y1t, and a z1t? So it could be moving back and forth, up and down, and towards you and away from you, all at the same time. That would be adding just a third dimension to that parameter, x, y, z, in terms of time. So parametric just means parameter, and for us, parameter will be time. We will look at polar graphs very similarly. With polar graphs, if you remember theta and r, like r depends on theta. But we treat theta almost like a time, sort of. But really polar is also another type of parametric graph. Yeah. Okay, other follow-up questions. We're going to continue to kind of develop these, but this is sort of an intro with the calculator to kind of get you going on what this is. We're going to do a little bit of graphing by hand even, and we'll kind of move forward from here. Unless you have other questions, let me just summarize. Like your question of like, all right, what are parametric functions really? To summarize, this is really no different than a particle moving along the x-axis, but now it gets to move up and down at the same time it's moving left and right. I mean, that's the condensed version. That's it. And so the x describes the x motion, the y describes the y motion. They both depend on time. Okay. So let's keep going with this. As far as, oops, I keep doing that. In our notes, so if we kind of scroll on down here, just an overview. this will kind of summarize what I was just saying. Here we go. So a parametric equation is an equation in which x and y are both dependent variables. Typically, they both depend on, this is a review, I just said this. They both depend on time or t, that's right. So occasionally, often, I don't know, sometimes that parametric graph will fail the vertical line test. Y does not have to be a function of x, but both y and x are functions of t. And when put together, you get kind of a unique graph, like you just saw. Okay, so for the next examples, we are going to make tables of values. We're going to be sketching a curve, and we have to indicate the direction of motion for the graph. And then we're going to talk about how we could sometimes eliminate the parameter and compare what we've known from the past to what we're working on right now. So I want to do this first one with you guys, and then I'll mostly turn you loose on the other ones, and I think you're going to do great. So let's take a look at that first one right there. How this works is really how we typically have done things. We're gonna do some plugins, inputs and outputs. The t's are going to be your inputs. The x's and the y's are going to be your outputs. So for this first one, x is equal to 2t minus 1, and y is equal to 1 minus t. What would you say our t step is? 1, right? From negative 1 to negative 2, 0, 1, and 2. Those are all 1 apart from each other. I don't know why I flipped around the negative 1 and the negative 2. We probably should put those. Let's mentally flip those to where they should be, right? Numerically speaking. Right, if we're going to go down the table, it should go negative 2, negative 1, 0. Yeah. So, I don't know what I was thinking there. Maybe I was distracted. Here we go. If you plug in a negative 1, what is your x? Negative 3. And what is your y? 2. So my first point is negative 3. Actually, this will be technically my second point, won't it? Because I do usually know how to count. All right, so negative 3, 2 is right there. Okay, so let's do our first point now. So if I plug in a negative 2 for t, what is my x and my y? Negative 5 and 3, right? Yeah. Okay, so negative 5 and 3, so 1, 2, and 3 is right there. Like, how do I what?
Do you plug it in at negative 2 on the graph?
So t is negative 2. This I want you to notice, this is definitely, I think, getting to your question. This is still the x and the y axis. There is no t axis. T is sort of an invisible variable. It's the parameter. X and y both depend on time, but there is no t axis. There's just an x axis and a y axis. All right, so when you plug in a 0 for t, what do you get? Negative 1 and 1. Question, Hayden? Okay. Negative 1 and 1. When you plug in a 1, what do you get? 1, 0. Starting to see this pattern, I think. You plug in a 2, 3, and negative 1. Yep, agreed. So 3, negative 1. And we'll connect those. Well, by connecting them, we're like reducing our t step down to being really, really small, right? And we're going to put the direction of motion. So I know I started in the upper left, so I'm going to draw my connection there. The way that I indicate the direction of motion is to put these little arrows. You just technically only have to put one arrow. But this particle is moving down and right. That's the direction of its motion. Okay, what do you think? Isn't that what the calculator was just doing a second ago? Didn't really show you the direction of motion unless you were watching it move. Then you could see it. But here we put the little arrows on there since it's kind of a static graph. Okay, and then finally eliminating the parameter by substitution. Bless you. What did I say the parameter was for these? T. Yeah, x and y both depend on time. So to eliminate the parameter, that means the result of this means there should be no t, right? If it's eliminated, it's gone. We're going to use substitution to do that. So what I think I'll do is I will take this right here, y equals 1 minus t, and I will solve it for t. So it would be, what, 1 minus y equals t? Okay, so I'll do this down here at the bottom. So it'd be 1 minus y is equal to t. And then I'm going to take that 1 minus y, and I'm going to put it in for the t in the other one, in the other equation, the x equation. So if I do that, I would end up with x equals 2 times 1 minus y minus 1. And we got a little cleanup to work. At this point, we've eliminated the parameter, technically. But I'm going to clean this up a little bit, get it into a more familiar form, see if it makes sense to us. So it'd be x equals 2y minus 2 minus 1. I'm going to go ahead and solve this for y, right? Because that's kind of the typical way we see these sorts of things written. So it's going to be x plus 3 is equal to 2y. Dividing by 2, I'm going to get 1/2 x. Something doesn't make sense.
2 minus 2y.
2 minus 2y, there we go. Oops. Thank you. 2 minus 2y, so that would make this a negative 2y. So it would be negative 1/2 x. And that wouldn't be a 3 anymore. That would be a 1. Sorry about that. Let's see here. 2 minus 1 is 1, so that would actually be minus 1, wouldn't it? Did I do that right? I messed myself up. I'm going to go all the way back here and unmess myself up. There we go. So that part is right. So it would be x equals 1 minus 2y. Okay, yeah, this is going to work. So x minus 1 equals negative 2y. So I'm getting negative 1/2 x plus 1/2 equals y. Okay, so what kind of a graph is that going to generate?
A line.
Yeah, and what's the slope of that line?
1/2.
Negative 1/2. That's why I knew I'd messed up, because I could see the slope was supposed to be negative, and I somehow got a positive, right? So I knew I'd messed that up. Yeah, negative slope, a y-intercept of 1/2. Does that make sense with our graph too? Yeah. So what you've just seen is there's more than one way to graph a line. We just started with parametric graphs, right, with an x and a y, both in terms of t. Yet we ended up with something that an Algebra 1 student could do, right? You guys could have done this 4 or 5 years ago, no problem. And so sometimes you can eliminate the parameter, sometimes that is a useful thing, other times it's not. Sometimes it's not even possible. Most of the time, eliminating the parameter won't be a big thing. I just wanted you to kind of see the connection with what you've done in the past with what we're doing right now. Okay, you good? Why don't you guys try the next one? You can do the next one on your own. Let's fill out the chart here. I'll fill it out quickly. You guys, I'm sure, have already done this.
It's a parabola. Yeah.
Yeah, it kind of goes off the top on the last one, doesn't it? So did you guys get those points? 0, 1, 1, 2, 2, 5, 3, 10, and 4, 17?
417 doesn't fit though.
I know. It's okay. It's okay.
When's the homework due?
Say again?
When's the homework due?
I think I have it set up right now as...
June to the 17th.
I think I have it set up as being due the day of the quiz, since it's all paper-based.
Ah.
So, did you guys get something like that? Hello? Yes?
Yep.
Okay. So if you connect those, essentially what you're doing, of course, what you're essentially doing when you connect them, you are making your t step really small, which is okay. One thing you don't want to do, let me make this a note here. One thing you definitely don't want to do is you don't want to put arrows on the end of this. To indicate the direction of motion, you want to put an arrow or two on the graph itself. But putting arrows on the end of it indicate that it keeps going. It doesn't, right? Your t parameters were from 0 to 16. That's it. You can't assume anything else about that. So put, endpoints on it and then indicate the direction of motion with those arrows. And then as far as eliminating the parameter, did you guys just square both sides on the x equals root t? So if you do that, of course you get x squared equals t. And then you could just plug that in directly. You get y equals x squared plus 1. We all heard Hayden earlier say it's a parabola. Technically, isn't it just the right half of a parabola? Technically, the left half did not get graphed here because of our t parameter, our t domain, I guess you could say. But that's it. Now, are you guys feeling a little more comfortable with this? You've had a chance to see this on the calculator. You've had a chance to do this by hand. Is it okay? It's brand new, isn't it? More or less? Okay. Hopefully it's going okay for you. Let me look and see what we got. Guys, please notice here the t's were not supplied to you, but it does give you a domain of... Oops, let me try and draw a little more precisely here. -2 to 3. So if we go -2, -1, 0, 1, 2, 3, fits in there. So a t-step of 1 for us makes sense. All right, so you got x equals t squared minus 2, y equals t over 2. See what happens. It's the most interesting graph yet, maybe? At least the ones we've done by hand. So check that table there. You guys get the same sort of stuff? All right, I'm going to go ahead and graph it then. We'll see what this looks like, and then we'll get on to talking about your final. So let's see here. I've got, 2, -1. Right about there. -1, -1/2. Right about there. -2, 0. Oops. Right about there. -1, +1/2. That's not quite right. Right about there. And then 2, 1. And 7, 3/2. So 4, 6, 7. Does that work for you guys? What do you see? Yeah, sideways parabola. Now the direction of motion is really important here. If we go, the t increasing as you saw there in the table from -2 to 3. You draw something like this. Let me try that again. I kind of missed that last point. There we go. The direction of motion would start off going up and left, wouldn't it? At some point in there, it starts going back to up and right. So it takes that direction of motion right there. Those little arrows tell you to start down below and kind of go left and up and right. It was going up the whole time, but it went left then right. This is kind of similar to the first one we looked at on the calculator, really, as far as the back and forth and up stuff. Okay, and then did you guys eliminate the parameter? So a pretty quick one to do as far as that goes. I think I would just take this y equals t over 2 and just say 2y equals t. And then I could plug that in and say x equals 2y quantity squared minus 2. So x is equal to 4y squared minus 2. And you can see that's kind of the classic sideways parabola. It opens to the right, but it's been shifted left 2. It's pretty skinny, vertically speaking, right? Scrunched vertically, I guess you could say. So that's it. Introduction to parametric stuff. Are you feeling okay with that? This whole chapter is about parametric stuff. We're going to look at vectors. And believe it or not, vector is going to depend on time. Later on, we'll look at polar. Polar will depend on theta. It's similar enough stuff. All right. So if your phone's not in the